Now that, due to memory management techniques, the physical location of a process in the main memory poses no problem to its execution, can we try to achieve something more? That is, run a process which is even greater in size than the physical memory? That is, can we achieve virtual memory? That is our topic of discussion today. Now, the virtual memory that we would like to achieve, let us see what is the scenario. Here I have shown few components of our system that we will need. This is a physical memory. Only 6 frames are here. I have assumed that these 2 frames have been taken by the operating system. Frames 2, 3, 4 and 5 is available for the process. I'm assuming there is a single process and the virtual address space is of 8 pages long, right? Now what we have done is that we have brought into the picture the disk, the secondary storage or direct access device as we call it. What we have done here is that a copy of the process, okay, the entire virtual address space has been kept in this storage, secondary storage. Okay. Now I have shown it as if it has been kept in a sequentially like that. We'll see later on the situation may not be like that when we discuss information management. Now here is the page table for this process. As I said, there's a single process I'm trying to run. You can see the size of the entire process of 8 pages. Here we have only 4 frames that is available to run this process. Let us try what happens. Say the process starts executing in the page 0. Since it's page 0, and say that page 0 is loaded into the frame 2, and therefore the page map table will contain 2 here, right? And we do this, that we take the page 0 from the disk, load that into the frame 2, make this page map table this 0th entry 2, make this valid bit 1. Initially we make all the valid bits 0, we make this valid bit 1 and then transfer control to page 0 at the point where the execution should start. Now the process starts executing. Sometime after some time, when it finds that it needs another process, say another page, okay, say now the page 4 is needed, therefore then page 4 is brought here, right? And at the 4th page, the corresponding frame number, that is, sorry, 4th page, the corresponding frame number 3 is inserted, the valid bit is made 1 and the execution starts once more. After some time, assume that page 7 is needed. Say page 7 is loaded. Oh, sorry, it was in the page 3. Is it okay? Therefore, it's okay that page 4 is in frame 3. Now, say page 7 is needed. Say page 7 is loaded here. Therefore, at the 7th page, okay, we enter the frame number 4, make the valid bit 1 once more. And after some time, say page 2 is needed. Therefore, we load page 2 here. When you load means we take from this disk storage and load it over to here. in the corresponding frame, and that page 2's frame number turns out to be 5 and the valid bit is 1. Okay, it goes on continuing. Now, as long as the process remains in the page 0, okay, page 2, page 4, and page 7, as long as the execution point of the process remains within that 4 pages, we do not have any problem. But say now, while executing, the process needs, say, the page 3, okay, page 3 is here. So if the process needs now the page 6, right? Now, see, the process now needs the page 6. What will happen? There is no memory that is left. The process needs the page 6. No memory is left. Therefore, what we do is that we take one of the pages that is in the memory, right? Replace it by means of the page 6. Say, for example, that we take out, say, page 4, right? Then insert page 6 here, and therefore page 6 is now in frame number 3. This bit, valid bit, we make 1, and this particular, that page 4 is no more in the memory, and therefore we make this valid bit to be 0, which indicates therefore now that page 6 is there in block 3, I mean in the frame 3. Here is the frame 3, page 6 has been brought, page 4 has been replaced with page 6, and therefore that 4th entry in the page map table is updated to denote that that page is no more there, and the 6th entry of the page map table, the valid bit is made 1 to denote that that page is here. Now, that is the picture that we have, which means at any instant of time, the page map table gives me not only the mapping, but also gives me what are the pages that is there in the frame, in the physical memory, in which frames, okay, by means of this valid bit. Now, bringing the page from the backup storage, not the backup storage, from the secondary storage, the disk, into the physical memory, right, we call it swap in. Now, one problem may be there. The problem is that we have replaced page 4 with page 6 in the frame 3, but page 4 may have been altered, may have been modified, may have been written into. In that case, if we simply remove page 4 by page 6 and do nothing, so far as the copy here is concerned, or the copy here is concerned, the status that will be shown over here is wrong, okay, it's erroneous. Therefore, what is done is this, that if during the time that page 4 was brought in, that means swapped in, and the time the page 4 is removed from the physical memory, if there is a change in page 4, that is reflected in this column of the page map table, which we call the change column or the change bit. For example, if the page 4 was changed, then that will be made 1. Otherwise, it will be 0. For example, if page 0 was not changed, then it is 0. If page 2 was changed, this should be 1. If page 7 was not changed, right, then it is 0. And if page 6 is changed, then it is 1, right? Now, while replacing, say, page 4 with page 6 in frame 3, if it's found that the change bit is 1, that means the page 4 was changed. In that case, the page 4 has to be written back into the backups, into the secondary storage. That means page 4 have to be written back here into the secondary storage, so that when that page 4 is brought in once more, or execution is over, page 4 reflects the correct status. Now, this is what, in fact, in effect, the mechanism that has to be performed to achieve virtual memory. You see, at any instant of time, since my physical memory is limited to only 4 frames, only 4 pages I will keep. When a page is necessary, that page will be brought from the disk storage and will load it accordingly. Which page at any instant of time is valid, okay, which mapping is valid is given by that valid bit, and if there is any change, okay, in that page during the time that that page was in the memory, that change is reflected in the change bit. That change bit is consulted when you swap out, right? Therefore, the entire process depends upon swapping in a page and swapping out a page if necessary, okay, as is needed, which essentially means that one need not restrict it so far as the program size is concerned, the process size is concerned, to the size of the physical memory itself, right? We can write a process which is quite big, even bigger than the physical memory, okay, as long as the addressing mechanism of a translation or of the CPU, okay, that means the virtual addressing supports it. You keep that entire copy of that program or the process in the disk. You bring only the relevant portions into the memory. That is reflected by the status of the page map table, okay, and you start executing it. Now, that is quite fine as far as the mechanism is concerned, but can we really do it, okay, without affecting the total efficiency, total throughput too much? The answer is yes. Why it is yes? That I'm showing by the plate that I showed long back while I was discussing cache memory. You know, the principal locality remains valid. What is the principal locality? The principal locality is that we have the temporal locality, that locality in time, which says that if an item, that means this reference, it will tend to be referenced again soon, right? Which essentially means that if you are in a program, in a process and executing some instructions here, then you tend to execute instructions nearby. So for example, if you are accessing data somewhere here, you will tend to access data nearby, say arrays, generally accessed, okay, sequentially, right? Therefore, this is the temporal locality, that in time, that as the time progresses, you will confine to the locality near the current reference. Similarly also, the spatial locality, that is locality in space, that if an item is referenced, the items whose addresses are close by will tend to be referenced soon, okay? That means if I have accessed something here right now, I will access something nearby, okay, the next time frame, okay, which is more plausible, right? Now, if this principle of locality is valid, right, which is valid, which has been seen to be valid, then the entire thing, that virtual memory can work without much loss of efficiency, with a marginal loss of efficiency, right? Now, this is achieving virtual memory and executing a process, okay, whose size is far greater than the physical memory that is available. Now, what happens if there are more than one processes, okay? That is a picture that I've tried to show in this plate. Here you see that there are three processes, J0, J1, and J2. At any instant of time, the current status I have shown, right? So, example, that J0's page 0 is in block 2, J0's page 3 is in block 5, J1's page 2 is in block 4, okay, and J2's page 4 is in block 7, and J2's page 6 is in block 8, okay, and these three processes are being multi-programmed, right, and therefore being executed concurrently. Now, say at this time, what happens that say this process J0 needs another page, say page 1. There is an empty space, say 3. Let that be allocated to this J0 page 1. Therefore, it is now J0 page 1 here, right? The valid bit is made 1, and the change bit, depending upon whether there will be any change or not, it is now 0, depending upon whether any change will be made or not, the change bit will change. Therefore, while bringing in it, we make the valid bit 1, change bit 0, and accordingly we do it, right? Now, say this, we switch from the process, the operating system switches from the process J0 to say J2, and page now, while executing J2 needs a page 2. Now, only one frame is available, 6, therefore, page 2, the 6 is allocated, J2, page 2 comes here, the valid bit is 1, change bit is 0, quite fine. J2's process goes on executing, so no problem. And then say we switch over from J2 to J1, and the J1 now needs, okay, a page, say 0, and there is no page, no frame that is available over to here. Then what we do? What we do exactly that what we did in the single process case. We try to find out a frame, rather we find out a frame from where we swap out one of the pages of one of the job into the disk storage, right? And the required page of J1 is brought in over to here. For example, say if that 08 page of J1 is needed, maybe that we decide that page 2 of job J1 will not be needed in near future. We swap it out, right? This thought is J1 P2, right? That was only J1 P2, this only page was here. Anyway, so for example, this we decide to swap out, right? Therefore, we swap out this page. This will be a bit of a problem. Therefore, let us keep this page, say J1 P2 here, choose another page, say J2 P2, right? Or J2 P2 has been brought very recently. Therefore, why not say J2 P6? This page we take out, swap out, and this 8 we put over here. Change the valid bit is made 1, change bit is made 0, and this we say that job J1 page 0 is swapped into the frame 8, and J1 starts executing, say, once more. Okay. Now that way you can see that whether it's a single process or whether it's multi-programming, that multiple processes are being executed concurrently, the same thing that we can apply, that is that we only load the relevant pages of a process that is required for the execution of the process, right? And if a process while running needs a page which is not in the memory, we bring that page, swap in that page from the secondary storage. If there is an empty frame that is available, it's quite fine. If there's no empty space available, then we forcibly free one frame, and if that particular page which is being forced out has been changed, then that page is written back into secondary storage, and the new page is brought in, and the process starts once more. Okay. Now, this situation is called a page fault. Okay, page fault is that the process is executing, it now needs a page, and it finds that page is not in the memory. That means page entry in the page map table is not there. There's a page fault. And at page fault, certain action has to be taken. And the action is that bring the page. And for that, do whatever you need. If your frame is there, empty frame is there, you use it. If no empty frame is there, then you forcibly make one frame empty and then use it. Naturally, therefore, one thing comes into the picture, that what should be, I should say, that that replacement algorithm, right? We'll talk about this replacement algorithm and exactly in somewhat more detail how page fault is handled just after some time. Okay. Let me show the plate that we showed you earlier when we discussed the cache memory. Here's the memory hierarchy. The different registers memories have been shown. Their access time, post per megabyte, and the capacity in bytes have been shown, right? The CPU registers are there, then cache memory, static RAM, main memory consisting of dynamic RAM, the disk storage, and the tape. the access types are random up to this, direct here, and the sequential here. Access time is 1 to 3 nanosecond, 5 to 25 nanosecond for the cache, the SRAM, 60 to 120 nanosecond for DRAM, 10 to 20 millisecond on the average for the disk, and 20 millisecond to say 10 seconds for the tape, since this is essentially a sequential access, right? Cost per megabyte, naturally pretty high here, $100 to $200 here, $5 to $10 here, $0.1 to $0.2 here, and $0.02 here. And the capacity, the lower ranges I have shown, the lower limits I have shown, now it is much greater than that. Say few hundreds to few thousand, the CPU registers. Here 256 kilobyte onwards for the cache, 16 megabyte. Nowadays it is quite, even for PCs is 64 megabytes onwards, say. It's 8 gigabyte for the disk and 1 terabyte over to here. Now, in the case of our cache memory, what we intend to achieve is the speed, the access time of this cache memory, that SRAM, and the capacity of the main memory at the cost of the main memory. Therefore, to achieve that access time of cache, the capacity of the main memory at the cost of the main memory, that was the purpose of putting cache, and we showed that we are pretty successful there, okay, as long as that hit percentage, that hit ratio is pretty high, okay. Similarly, in the case of a virtual memory, what we are trying to do is that more or less an access time of that main memory, the capacity of the disk at the cost of the disk, right? Therefore, as if in the case of a cache memory, we are trying to zoom out that cache onto the main memory. And in the case of a virtual memory, we are trying to zoom out main memory onto the huge disk that we have, right? Now, how much we are successful, that we'll see, okay? Naturally, one thing is that from the point of view of the principle of locality, we definitely have some success. And what is the success? What we'll try to make a measure out of it. Now, let's discuss the memory hierarchy, show the memory hierarchy once more, where we showed this plate also earlier, where we have shown it as a pyramidal structure. Here are the CPU registers, right? Lower in number, but higher in speed. The speed decreases this way, right? Size also, but size increases this way, okay? Then we have the cache, then the main memory of higher size, lower speed, magnetic disk, still higher size, lower speed, and MAC tape, definitely quite higher size, but once more quite a lower speed. We're trying to achieve the speed of cache, okay, and the size of main memory while executing a program, right? Best is if we could have increased the registers, okay, but that's not possible due to the cost, and therefore the limit has to be set, right? In the cache, we wanted to achieve the speed of cache and the size of main memory, and in the case of virtual memory, we're trying to achieve the speed of main memory, right, and the size of the magnetic disk, right? And the magnetic tapes are generally used for the backup or archival purposes, as we said earlier, right? Now, that is the situation, therefore, and that is what is our objective is. Now, let us see that what are the, a little bit in more detail, that what are the things that is involved over here. Now, just to have a clear picture, we recapitulate the paging hardware. What we did in the case of a paging hardware, this is a familiar picture by this time, that the page of the virtual address, the page number, is first checked at the TLB. If it's a hit, then that is sent to the multiplexer. If it's a miss, then the page number is consulted, okay? The page table is consulted. At that page number, the frame number is taken. And either this or that, depending upon hit or miss, is routed into that physical address, page is replaced by frame. This gives me the physical address, and we come to that physical location to access the particular location, right? Now, let us see, in our case of our virtual memory, what we'll have to add to it, okay, add to this process, and that has been shown by means of this diagram, okay. What we have done here, you see that, say, we start that instruction, the virtual address is generated, okay, while executing this instruction, even including fetching, the TLB is checked. If it is a hit, yes, then we come over and generate the physical address. If it is no, that's not a hit, then page table is accessed, okay. Then it is checked that whether page in main memory or not, because now I'm talking about the virtual memory, the page, that particular page may be in the memory, may not be in the memory, and that is dictated, okay, and that is shown by means of that valid bit. Now, if the page is in main memory, it's quite okay, then we update the TLB, generate the physical address, and naturally go ahead with it, okay. But if it is not, that means not in the main memory, no, then immediately, as we say, that page fault trap takes place, and the page fault trap handler is immediately activated. We enter at this point of the page fault trap handler, okay. Here we check the page fault handler checks that whether the memory is full or not. Okay, if the memory is full, right, then we go by this. The memory is not full, that means some frame is empty, then naturally we come by this. Here we transfer the missing page from the disk to memory, okay, update the page table, and go back to the start of the program once more. The instruction started once more, right? This instruction started once more means the instruction is fetched and started executing once more. Okay, let me repeat that page fault handler. If memory is not full, that means frame is available, empty frame. Transfer the missing page from the disk, update the page table, go back here. But if the memory is full, then we select a page for replacement and check whether the change bit is 1 or not, okay, of that page which has been selected for replacement. If the change bit is not 1, that means that it has not been changed, then we go here, transfer the missing page from the disk to memory, update the page table, and come over to here. But if the change bit is 1, that means that particular page has been written, has been modified after it was brought last time into the memory, physical memory. Then we'll have to swap back, okay, write back the page into its proper place in the backup storage, and then only we can transfer the new page, update the page table, and go back. Therefore, here the write back is necessary, but here the write back is not necessary, depending upon the change bit. This is the trap handler, okay, page fault trap handler that is activated. Now, naturally, that next question arises as to that when should we bring a page, right? When should we bring a page? Should we try to bring some pages, okay, initially and keep it in the memory and start it? Now, what we can do is that, or we bring a page one by one. What we can do is this, that we bring a page into memory only when it is needed. That means only when a reference is made to it, okay, only then that page is taken from the backup storage and is swapped in. The reason is that in that case, less IO is required, okay, because for the pages which may not be needed, no use bringing it into the memory, and therefore use time in input-output. Less memory is needed, more processes can be accommodated because less memory is needed per process, and faster response due to less overhead. I mean, when I say that faster response, that means the throughput of that entire system, right? And a page is needed when it is needed, when it is referenced. Therefore, a page, when it is referenced, only then, if it's not in the main memory, then only it is brought into the main memory, and that is why we call it that is a demand paging, right? On demand, the page is brought into the memory. Now let us try to compute our effective access time, right? As we did in the case of our cache memory, let's try to compute that effective access time. We're assuming a page fault rate, P be the page fault rate, okay, which lies between 0 and 1. If P is 0, naturally there is no page fault, okay. P is equal to 1, then every memory reference generates a page fault, right? Actually, the value should be between 0 and 1, and it should be closer to 0. As close to 0, the performance will be better. Then let's see that what should be that effective access time, EAT, okay? That effective access time, or EAT, is 1 minus P into the main memory access, okay, plus P into the page fault overhead, right? And the page fault overhead is page write back time, page reading time, plus the restart overhead. That entire thing is the page overhead. Let us try to compute, okay, for some data. Let me assume that memory access time is 200 nanosecond, a bit higher possibly. Okay, page fault rate is 0.1. Page written or write back time is around 10 milliseconds, and in 50% of the cases, write back is necessary. Then that EAT will be 1 minus P into 200 nanosecond, 1 minus P into 200 nanosecond, plus P into 15 millisecond, where I have just ignored that restart overhead. That page write back time I have taken, page reading time I have taken, and since the 50% of the cases the write back is necessary, I have taken to be 15 milliseconds. And you see, if you compute it out, it turns out to be 1.5 milliseconds, right? And you can immediately see that it's pretty high, very high, okay? The CPU is going at a tremendously fast rate, right? Whereas, if you go by that effective access time, it turns out to be 1.5 milliseconds with this figure. You know, it is going as if at the speed of a bullock cart, and the entire efficiency will fall. Then, what is the advantage of having, say, this virtual memory? The advantage cannot be derived this way. What has to be done is that essentially we are doing multi-programming. So when this page fault interrupt, especially this I/O, that means write back and transferring from the disk, which is in fact the most time-consuming aspect of that entire thing, say 10 milliseconds. When this is done, this particular process is taken out of the running state and put into the wait state, as we have told already. Okay. Another process which is in the ready state is brought back into the execution state or the run state, right? Therefore, this effective access time is not to be seen in this way, okay? Right. It is not that the CPU has to remain idle. The CPU has to remain idle, and that effective access time turns out to be 1.5 milliseconds. There's no use having virtual memory. The concept of virtual memory turns out to be immediately practical, pragmatic, only in the case that when this particular swapping in, swapping out of pages is taking place, that particular process is put to the wait state, and a process from the ready state is brought into the running state, right? That is where the success of virtual memory do exist, okay? Now, so far as this is what is our mechanism of achieving virtual memory is concerned, but you see that while achieving virtual memory, we need to have page replacement. Okay, it will be very seldom the case that the frames will be available, frames will remain empty, and therefore some page replacement algorithm is to be brought into the picture. Now let's start the discussion on the page replacement algorithms. Objective naturally is to achieve lowest page fault, right? Now let's see how we try it. First, let us talk about an optimal algorithm. Okay, in that optimal algorithm, we try to replace a page that will not be required for the longest period of time in future. The best is if that page is no more required at all, but that may not be the possible. Therefore, we try to find a page for replacement to bring a new page which will not be needed the longest amount of time in future. For that, we have taken a page reference string. So this is a page reference string as an example. So this is the way particular process is asking for pages as the memory is being referenced. Okay, the logical addresses are being generated. So page 1, then page 5, then page 4. The green numbers, the string of the green numbers shows the page reference string. Assume that when we start with, no page was there in the memory. Therefore, you see when the first page was brought in, that means we have started execution at the page number 1, there will be a page fault. Then page 5 is being brought in, there will be page fault. Page 4 is being brought in, there will be page fault. Page 2 will be brought in, there will be page fault. Once the page 1 is referenced, there will not be a page fault because 1 is already there, right? Here we have, say, the 4 frames. If we assume that the 4 frames are there, that means by 4 frames I mean as if 4 frames of main memory has been allocated, right, for this process. Then here we have, these are the pages that are there. Then when page 1 is referenced, it's already there, no page fault should be there. Now when page 5 is referenced, the page 5 is there, and therefore there will be no page fault. And now say page 3 is referenced, page 3 is not there in the memory, therefore some page has to be taken out and page 3 should replace that page. Okay. Now we see that if we could see the future, we see that page 2 will not be needed, okay, in close by time. And therefore, why not take out page 2 and replace page 2 by page 3, so that now the physical memory contains these pages 1, 5, 4, 3, and we proceed. Page 1, then page 5, then page 4, all of them are here, and therefore we do not need page replacement. Now page 2 is referenced, and since page 2 is not there, therefore either you can do that, I can take page 1 or page 5 or page 4, replace it by page 2, okay, and then go ahead once more. And since the process ends here, no more page replacement is necessary. Now here you see that number of page faults is 6, which is a measure, okay, of that efficiency of a replacement algorithm. Here we have assumed that whenever a page fault has happened, say here, we can see forward, see in future what are the pages that will be needed, and decide about a page, okay, which will not be needed in near future. But naturally that is not practical, that cannot be done. But this is the algorithm which can be used for measuring the performance of the practical algorithms, right? And that is why we call it an optimal algorithm, which possibly only uses that for this, that means measuring performance of other practical algorithms. Okay. Now let's see one practical algorithm. We call it that first in, first out FIFO algorithm. Here we have assumed that 3 frames are available, and that is shown here, that these are the 3 frames that is available for this particular process, right? This is the reference string. The same reference string we shall be using for all the algorithms. That means it is a green string that I've shown for that optimal algorithm, right? Here it has been shown in the pink. Page fault has been marked here. Let us see. Initially there was no page in the memory. Page 1 has been referenced, brought. A page fault is here. Then page 5 has been referenced. Page 5 is brought. A page fault here. That way, here is a page fault because 4 has been referenced. 4 is brought, and you know that our number of frames allocated is full. Okay. And now you see that page 2 has been referenced. page 2 is not in that memory, the page 2 has been brought in. Which page to replace? Here the algorithm or the criterion is a first in, first out. Whichever has come first should go out. And I see that as we are bringing in pages, the first in is always at the lowest. Okay, therefore this one goes out, the page that is going out has been encircled. Okay, therefore this page 1 goes out and page 2 comes in. All right. Similarly, when now 1 comes, you immediately see that there is a page fault, and therefore the page 5 goes out, 1 comes in. Then page 5 comes, page fault, page 4 goes out, page 5 comes in. 3, okay, there's page fault, page 2 goes out, page 3 comes in, okay, and then it is 1, no page fault, 5, once, no page fault, 4, there's no page fault, there is a page fault, page 1 goes out, page 4 comes. Similarly, there is a page fault, page 5 goes out and page 2 comes, right? You see here that there are 1, 2, 3, 4, 5, 6, 7, 8 and 9 page faults. Okay, this is a contrived example. In fact, chosen so that the number of page faults turns out to be higher, so that as an example it can be shown. Naturally, the page fault cannot be that high, okay? But for this particular reference string, a contrived reference string, the number of page faults is 9, right? Now, if we take the FIFO algorithm for 4 frames, the same reference as the 3 frames here, okay? Instead of 3 frames being allocated here, we have 4 frames have been allocated, right? And we apply that FIFO algorithm once more. And you see that initially up to the 4th frame, okay, 4th reference, there will be all page faults because new pages are being brought in on demand, right? Then there is no page fault here, no page fault here, right? But there is a page fault, 3 comes in. Here is a page fault, okay, 1 comes in. Here is a page fault, 5 comes in. Here is a page fault, 4 comes in. Here is a page fault, 2 comes in. And here is a page fault, 3 comes in. And we see, let us see the page fault, number of page fault. You see, the number of page fault here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10. The same reference for 3 frames allocation, that means smaller size of memory allocated, we have 9 page faults, and for higher number of physical memory, higher size of the physical memory allocated, the number of page faults increases. This is called, in the case of a FIFO algorithm, is a Bellardi's anomaly, after the person who first noticed it and reported it. Okay, this is called that Bellardi's anomaly. Okay. The anomaly is that you increase the number of frames allocated to a process, increase the memory size, the number of page faults increases, okay, which should have been decreased. Okay, this was noticed and reported, and that is, say, one important aspect of the FIFO algorithm. Now, naturally, this is not the only algorithm, the FIFO algorithm for page replacement. There will be all other algorithms which we will be discussing in the next lecture. Okay.